Good morning, good afternoon, good evening, wherever you are. Welcome today to the Scaling Embedded ML AMA. Today is going to be a fun day because we have an exciting set of people that we brought together. And some of these people will be people that you would actually recognize in a heartbeat, but they're domain experts that are coming in from embedded machine learning. And one of the key things that we want to try and achieve in today's AMA is try and give you an opportunity to actually ask interesting questions with some of these experts that we have. I'll talk about the thematic way we kind of align today's AMA so that you sort of understand the context for why we're doing the AMA. So first and foremost, we're all very excited about ML, and ML is increasingly moving towards the edge and the endpoint. That basically means dealing with small little devices that you can power, ML with basically a little coin cell battery. Now, while this is exciting, there are also really interesting challenges, both on the hardware side as well as on the software side. So today we want to talk a little bit about some of those opportunities and challenges that we have on the hardware side for embedded ML. Then we want to talk a little bit about the software ecosystem. And the software ecosystem would be about just getting models running on that device, but it could also be much bigger. In other words, it could be about how do you get ML to scale out on all of these devices? Because embedded ML is not about running an ML on just a single device. It's about actually having tens, hundreds of thousands of these devices scattered all over the place, and then being able to do machine learning at scale across all of them. So this raises some really interesting questions that I think the community would be excited to hear about in terms of addressing the opportunities and challenges. Now, I don't have all the answers. Nonetheless, there are people that we can get good answers from. So think of this AMA as an opportunity to understand where things are today and where things are going to go in the future. And hopefully we'll all learn something and then come back to another exciting AMA down the road. With that said, let me go ahead and bring the people in one by one. First and foremost, I want to bring in Eben. Awesome. There, Eben, please go ahead.
Good to be here.
Awesome. Introduce yourself, Eben, for a second, please.
My name is Eben. I'm that's my wife Liz. My name. Hello. 4 o'clock. 5 o'clock. 5 o'clock. 5 o'clock. Okay, right. 5 o'clock. You're live to the internet. There you are. Are you ready? See, I mentioned I have a hard stop at 5, and I said to Liz, who is our director of communications, please be ready to go. Really, to go at 5 o'clock, and it's got a number in, so it got her confused. So anyway, my name is Eben Upton. I'm one of the founders of Raspberry Pi. I run Raspberry Pi Limited, which is the bit of Raspberry Pi that does the engineering. And of course, the interesting thing that happened to us this year is we put a product into the market, a board level product into the market called Raspberry Pi Pico, which is seeing some interest. We're seeing some work being done in Edge ML. And we also made available the chip that powers Pico, RP2040, and that's gone into a number of products which are more closely tuned, I guess, to the needs of Edge ML users.
Awesome. Thank you, Eben. We'll be diving fairly deep into some of the interesting challenges around the various heterogeneous set of devices that we have around ML. So I'll come back to you in a bit. Next, we have Pete Warden from Google, who usually needs no introduction. Nonetheless, Pete, please.
No, thanks so much, Vijay. And this is awesome company to be in. So I'm the tech lead of the TensorFlow Lite Micro project, which is all about trying to provide the infrastructure to run machine learning on all sorts of really interesting constrained devices. Trying to fit in, just 20 or 30 kilobytes of memory is kind of the goal. We can't always quite diet that much, but that's what we're aiming for. And yeah, I'm really excited to hear what people have to ask and see what answers we can come up with.
Awesome. Pete's also the one who wrote the TinyML book, and a big shout out because I absolutely love this book. And it's obviously doing really well. And I think the most exciting thing about that book, Pete, really is the fact that I think it's made embedded ML at large just very accessible to people. So kudos and many thanks for writing that book. And of course, big shout out to Dan as well, who's a co-author in it. And last but not least, bringing in Jan from Edge Impulse. There you go.
Thanks, Vijay.
Could you introduce yourself?
Yeah, sure. That was a bit of delay. Hi, I'm Jan. I'm the co-founder and CTO of Edge Impulse. you're probably watching this on the YouTube channel of Edge Impulse. We're the largest embedded machine learning community in the wild world and probably outside of that as well. We got about 50,000 projects currently hosted on Edge Impulse, anywhere from anything with gestures data, the stuff with accelerometers, lots of audio, and even doing real-time image classification on a wide variety of things. So super awesome to be here, both with Eben and with Pete. We have super awesome working relations with both Raspberry Pi and Google, and naturally Vijay here, which we do a lot of stuff together with his team at Harvard. So it's an all-star lineup today.
Awesome. Oh yeah, and then on that note, I forgot to introduce myself. So I'm Vijay. I'm a faculty member at Harvard. My primary student is being an academic, but I'm also very, very passionate about getting cutting edge technology out in the hands of people. And like Eben, like Pete, and like Jan, we're all very excited about kind of just working together and kind of getting things out into the hands of people so we can actually see the next generation do amazing things. I mean, I honestly can't wait, because I think the future is yet to be kind of made. It's like, as much as all of us have kind of done bits and pieces of enabling the ecosystem, I think the key word there is enabling. I think what that future is really going to look like is going to be in the hands of many of the viewers that are out here today. So as you've kind of seen, we've got three amazing people down here. We've got Eben, who's going to talk a little bit more kind of centered on the hardware side. Then we've got Pete, somewhere in the middle, which talks about sort of having machine learning, how do we get machine learning models to run from a software sort of standpoint. And then we've got Jan on the extreme side, which is like, if you package these kinds of systems together, how do you actually move this into the ecosystem and try and solve real application problems, right? So that's the reason that we've got these three superstars down here. With that said, I'm just going to dive in first and say, like, what is sort of the interesting aspects around embedded hardware, Eben, just kind of talking about the device level?
I think what's happened, we've had an unusual experience here, right? Both with big Raspberry Pi, so classic Raspberry Pi, and with Pico and the many other RP2040 based products, in that neither of these platforms was intended as a machine learning platform. Now, obviously, we've been talking to Pete for the longest time, in particular, about, I think, all the way back to Raspberry Pi 1, right? And of course, the interesting thing with Raspberry Pi 1, which has got a 700 megahertz ARM11 single core ARM11 in it, is it's actually not that much more powerful. If you measure it in terms of its ability to do max, it's actually not that much more powerful than the Raspberry Pi Pico, which has a couple of 133 megahertz M0 pluses in. Obviously, it has more storage, but it's fairly similar in terms of compute. And none of these platforms were designed to be machine learning platforms, but there's been a kind of a coming together of the kind of the increasing performance of certainly of big Raspberry Pi. The increasing performance of big Raspberry Pi has kind of intersected this discovery on the software side and on the theoretical computer science side, that you can sacrifice that you only sacrifice relatively small amounts of precision and model performance in return for very large reductions in computation, in complexity and computation load. And it's really opened up, and on the big Raspberry Pi side, it's opened up, obviously, kind of these machine vision applications get run a lot. I mean, I always go back to the cucumber sorter. It's probably my single favorite Raspberry Pi example. Is a chap in Japan whose parents own a cucumber farm, and they're getting old. They're getting old, and they're sick of sorting cucumbers. And Japanese people apparently like their cucumbers sorted into a number of different buckets, a number of different 23, I think, was the number of grades of cucumber. And he built a machine using a Raspberry Pi and a camera and TensorFlow to classify cucumbers, to perform an initial 90 to 95% accurate classification of cucumbers into buckets. And so in big Raspberry Pi, you're seeing actual big machine learning applications. And then as this trend has continued, and then RP2040 and Raspberry Pi Pico have appeared, you're finding that at least the audio applications, as Jan mentioned, the audio and gesture applications, and the trimmed audio and gesture models actually fit very nicely into the amount of resource that you have on microcontroller platforms, certainly relatively memory-rich microcontroller platforms like RP2040. They fit quite nicely. You're probably still some distance away from vision applications fitting neatly onto those platforms, but it is a continuation. There's a continuation of a trend there, and of course, the platforms. As we continue to chase down process. The interesting thing about microcontrollers, you chase them down process nodes. Why do we have so much memory in RP2040? We have so much memory in RP2040 in that if you're going to make a 40 nanometer, if you want to make a 40 nanometer microcontroller, it's on a relatively advanced process node for a microcontroller, not for a mobile phone chip, but for a microcontroller. If you want to get enough periphery in order to put the pads down to get the number of GPIOs you want, you end up with this enormous sea of silicon in the middle, and you've got to fill it with something. And the easiest thing to fill space with is memory, so you end up with a lot of memory. Now that trend continues, and that trend will probably over time, along with further improvements on the theoretical side, will bring an ever broadening range of things within reach of microcontrollers, and that's super exciting. That's even before you started talking about putting accelerators in. We have a Raspberry Pi has an unusual relationship with accelerators. Because we apply a very brutal calculus to adding either features to the board or adding features into the silicon that goes onto Raspberry Pi products, which is effectively, if we have a feature that costs 10 cents, it's a 10-cent component, or it costs you 10 cents worth of silicon area, and it's going to be used by 10% of people. We divide through by the proportion of people who use it. And so we treat a 10-cent thing that's used by a tenth of people as a $1. It has to punch its weight like a like a $1 component in terms of its utility.
Eben, right there, right? Like talking about the cost. What is the general trend that you see in terms of the cost of these microcontrollers?
Well, that's interesting, right? Is that obviously the general trend of everything is downward. So last year, microcontrollers were a 28 billion unit market. In 2020, 28 billion unit market, and they were an $18 billion market. Now, that's really interesting, right? Because that suggests that microcontrollers are about 60 to 70% objects. Now, if you go out and you try and buy even at scale, and we do buy other people's microcontrollers at scale, you're going to try and buy a 60-cent microcontroller. It's not a very good microcontroller. And so it's interesting that microcontrollers as a whole are dominated by legacy, very low performance legacy kind of shrapnel microcontrollers. But what the really interesting trend that I think we're seeing, and then obviously up at the high end, you can buy a $10 microcontroller. You can buy a microcontroller which is more expensive than a typical application processor if you have particular requirements, say in terms of automotive grade and big Cortex M7s and stuff. But what's really interesting is what's happening in this kind of 50 cents, which is kind of the 50 cents to a dollar, which is kind of where RP2040 is, up to $2 or $3, you're seeing enormous amounts of performance, and you're seeing accelerators. Now, we have an allergy to accelerators because of that calculation. It's very hard to get an accelerator, either an external chip or an on-chip accelerator piece of IP, through that filter that I described. But you are seeing other people building chips with the kind of the ethos, particularly the ethos accelerators from ARM. You're seeing those start to crop up on chips now, and that does give you then that, and the increased amount of memory in the device does really give you the opportunity to run models which probably 5 years ago were firmly in the province of, I'm going to go run this on a graphics card, I'm going to go run this on a PC graphics card. Reduced complexity, somewhat reduced performance versions of those models are going to make their way down from hundreds of dollars of graphics cards down into a $2 to $3 thing. And what's good about that? You can deploy them everywhere. I'm talking not talking about hardware anymore. I'm talking about I'm all the way down, talking about all the way up, talking about applications. You can deploy these everywhere, right? You can embed intelligence into the world, and we see this, people do this with big Raspberry Pi at sort of $35, but you can embed intelligence, the return on investment calculation, when your platform costs, when your intelligence costs less than $5, your return on investment from deploying, there are many more sockets get created. You're not talking about companies taking sockets off each other. You're talking about the reduction in the capital and running cost of hardware, creating new sockets out of thin air, because you can, if your eye, we're talking about return on investment, if your eye goes down, then the threshold R goes down as well, and you get this, and it's not linear. You get this explosive growth in demand for compute and demand for intelligence, and that's what I'm really excited about for the second 10 years. We've been doing Raspberry Pi for almost exactly 10 years now. That's what I'm really excited for about the second decade of Raspberry Pi, being part of that explosion of intelligence. There we are. I've talked for too long, but I am super excited about this.
That's awesome. So I'm curious, talking about the application side, right? Like Jan and Pete, like, I'm sure both at Google and just externally in the ecosystem. I'm curious to hear your guys' thoughts on, with these devices getting really capable, what sort of interesting applications are we really seeing, like where industry is kind of playing? There's one thing where, we teach things and then we gotta get people excited in the academic world. But I'm really curious to kind of have you guys talk about the real world industrial applications for the community. Jan
Do you
and
want to
Pete.
jump in, Jan?
Pete can go first. He's our guest.
Yeah. So one of the challenges, and this is always a bit of a tease, is some of the most interesting stuff I can't talk about yet. Because it doesn't it hasn't quite made it out, but I can talk in in some of the more general terms. Like what's really exciting is seeing people being able to build things that make sense of the real world out there. So we're able to take things like, hey, here's a medical test. Let's actually kind of apply computer vision to the results of this medical test so that we can actually give more accurate results. Or, let's actually look at plant diseases and, apply plant disease, apply computer vision to, help figure out what sort of pests or diseases are present. Or let's, or even doing something more simple, trying to recognize when somebody's tapping on a board. If you don't have a button, but you have an accelerometer, it turns out you can do a really good job actually just sort of detecting double taps from users.
Yeah, really interesting Google paper that I read, which is Google put out this paper, which is effectively you can tap anywhere on the screen, or you can use pretty much a button. It's a virtual button. You don't need
a virtual button without requiring any sort of touch. It can be something that's sitting inside the case, and being able to kind of actually, suddenly anything with an accelerometer gets some extra free buttons. That's a really interesting, practical use case. The thing that drives me a little bit crazy is it's still not easy enough to do that. And a lot of that is on people like me and Jan, where Eben is, providing a lot of great hardware. How do we actually have the software and kind of the systems integration and make this stuff accessible? So I might
have you tried building this in a Jimples yet, Pete?
Exactly.
Well, this is an interesting question. I'm not sure which one of you to address this to, really, which is in terms of, we're an educational charity, right? We try and teach people about computers. And I had some of the best input that I've had when I've been working on this has been from Sophie Wilson, who's a former colleague of mine, and obviously is very famous for having created both BBC Basic, one of the co-creators of the BBC Micro, wrote BBC Basic, and then one of the co-creators along with Steve Ferber of the first ARM chip. And one of her bits of feedback to me early on in Raspberry Pi was that it was a flawed idea, and it was a flawed idea because we were teaching people about the past, right? That Raspberry Pi 1 with its single core homogeneous because it's single core architecture was teaching people about a model of what computers had been like in the 1980s and 1990s, and of course we mitigated this a little bit by at least being multi-core, still homogeneous but multi-core. Now the question is, what are we? So this is going to become we all believe that machine learning is going to become part of the toolbox for people writing software in the next. It already is to some degree, but it will really become part of the toolbox in the next 5, 10, 20 years. And the question is, what level of abstraction do we want to teach young people, children, primary, secondary, tertiary children, university students? What level of abstraction do we want to teach people that's going to, I guess, get us the best of both worlds, in that it will become part of the toolbox, but of course you use a tool best when you understand how the tool works. And how do we bridge that divide? Because I don't think I know how deep learning convolutional neural networks really do the magic. Where does the magic really come from? How do you think we should do that?
Staggered approach, right? It's not like any one size fits all. I think traditionally we try to think of this one size fits all approach, and I just don't think it works, right? Just earlier in one of the TinyML4D work groups that we have, we were actually thinking that perhaps it's a staggered approach where we'd say something like you'd have a no code approach, then you have a low code approach, And the third one would just be throw them in a Jupyter notebook, right? And I think the low code and the no code, I think, are the interesting aspects, because like the no code would be interesting. Like, we've had Scratch for a long time, right? So something like that is actually easy to kind of convey interesting application tasks. Then maybe we'd get into the low code. And I would say, Jan, I'm curious to hear your thoughts, because I would say like Edge Impulse, for instance, is a low code way of actually getting people to understand things, but you can still go and modify things a little bit, right? And then of course, then there's the extreme, okay, well, I'm just going to throw you into a collab that, you can do whatever. So Jan, how do you think about that sort of staggered approach?
My feeling is that the very first, and it's actually not just kids or whatever, or students that we need to teach this, but also to developers, embedded developers right now. Kind of the first step is how do you get this data-driven engineering approach in? For me, the only way that I can understand machine learning is that, like, normally I try to observe a pattern and I write code, and now I let the computer write the control loop, and I just provide the input and the outputs. It's like a fancy version of the solve function on my graphical calculator back in high school. But that requires good data and thinking about how to get the data and data quality control and all of that. So getting that stuff in and showing that, showing that data and the output have correlation, that machine learning can find that correlation, that is interesting. And a lot of the tools that we try to put together are about visualizing that, right? So we do kind of the 3D point cloud of your whole data set, and we try to separate it after some signal processing already. So no machine learning, but just showing what your data set looks like and whether it looks sane, and kind of tagging stuff that is, out of the ordinary. That kind of stuff, that helps a lot already, and in essence is even in commercial applications is 90% of the work, right? After you have all of that, then then training that model, that is a small feat at the end.
That's actually an interesting point. Yeah, I fully agree. Like, increasingly, Andrew has been talking about this shift from going from model centric to more data centric. It's really interesting because we've built a lot of tools around understanding what our networks do. This hodgepodge of neurons, you can even visualize which particular activation is kind of triggering which particular neuron, right? But for data, I think it's still this data science kind of thing, right? You need these data science degrees to understand very simple things like, what does your probability distribution look like of all your samples in the data? The simple distribution alone, people don't really know how to look at it. And I think it's because we have not yet put the emphasis on, look, you really need to understand your data. I feel like most people who touch machine learning will say, okay, I know how to have an 80-10-10 split, and that's about it. But that 80-10-10 split is really not enough, right? So I'm curious, Pete, obviously Google does an insane amount of work around this space, right? Just about understanding data. Like, what's your take?
So I actually just shared a link to some experiments that we launched at Google I/O. I think it's in our sort of presenter chat. I don't know if we can get it out onto YouTube. But what we did there was really tried to, I think about Scratch, and I still feel like that's code in disguise. Like, you're still trying to teach people how to build recipes to get the computer to do something. What is really interesting to me about machine learning is we have this chance for people to get computers to do what they want them to do by providing a bunch of examples, and kind of building on what Jan's saying about the data being the really crucial part here. What we tried to do with these I/O experiments was, first off, use the Bluetooth so that people didn't have to connect over like USB and UART, because that is a massive pain. Being able to use like CircuitPython and MicroPython, being able to use something as a USB drive where you drag stuff onto is kind of better, but doesn't allow much kind of back and forth communication. So what we settled on was actually using BLE and being able to connect over a web page to the board using WebBLE, and then really tried to have first off examples where people could just load up a web page, and within a couple of seconds they could just like play an invisible drum using kind of a pre-built ML model. But then once they'd had that kind of that first hopefully hit of, wow, okay, I'm actually using machine learning, we then just got them to do a few gestures, a few examples of gestures that they wanted to recognize themselves, trained the model on the web page in a few seconds, and then downloaded the model back to the board. And after that, somebody had actually, it's like, congratulations, you'd used machine learning. And trying to get that, first off, that very early kind of success, and that kind of success without having to force people into this kind of, I'm writing down a recipe for the computer to do something for me. It's like, you know, it feels like I'm hoping that it will reach a lot more people who wouldn't be amenable immediately to that kind of thinking and don't think that they are actually computer people, by like, oh, I can just give examples of what the computer should be doing, and it will learn from that and it will do it. Like, that is my holy grail. And, you know, obviously Jan and, you know, has, you know, some great tools and stuff around that. But if we can just get people who aren't thinking that they can do computers to have success.
Yeah, example-driven programming or something. Someone's got to come up with something new. Just about collecting data.
And compute, you know, one of our realizations in the first decade of Raspberry Pi is that there is only a relatively small number of people who are excited about computers. Computers, you know. I mean, you get me as a kid. You could have got me with a class on if statements. I would have been very much into attending that class. And one of the challenges is that's all of us, right, on this, on this chat. And what we have to remember. And I think we are most successful in teaching people when we remember that is not the dominant experience of learning about computers, and it's not the dominant motivation for the people who are learning about computers. The most successful motivation and the most successful thing you can engage with are people's problems. That people have problems that they want to solve, and computer platforms and computer education is most successful when it positions computing as a tool. As just part of the toolbox. And of course, this is an incredibly powerful omni tool. You know, this is the sonic screwdriver of computing. Of computing as tool. It's super exciting. It's super exciting. But you know, I think always the most important thing is, like, why are we getting people in? Well, we're getting people in because it's nice to help people solve their problems. So there is utility to that. But in terms of our ambitions, certainly Raspberry Pi's ambitions, to create a new generation of general purpose computer programmers who have the NAND to Tetris understanding of what they're using, which I have to say I don't when it comes to machine learning, and I've had to become very focused on the work that I do here at Raspberry Pi. If you want to have people with that NAND to Tetris understanding, you've got to put the rungs in the ladder between the NAND gate and the Tetris, or possibly the Tetris and the NAND gate. I don't know. That you have to, if you have to put the rungs in the ladder, and that's what I don't think I understand, and that I'm hoping to understand over the next year or two, is how you go from that data-driven world to a world in which people actually understand to the extent anyone understands what the models do, where people have understand the models or have an intuition for how they can build good models, even when they don't understand what they're doing, like most of us. That's the super exciting thing, because I think that will generate a generation of people with incredibly broad understanding of this field that hopefully makes Sophie happy.
I actually think that teaching them the data collection part, I honestly believe, is a lot easier than trying to get them to understand how to wire up a bunch of neurons, like, all these different layers and having all the low-level details, because data is something that we continuously kind of deal with in a way. I think if we can kind of build some of the tools that, like Jan was talking about, like the visualizer that Edge Impulse has, right, or like data cards and those kinds of things that Google has, I think a lot of people will be able to understand that. I think if we make the data part really tractable in an educational pedagogical sense, and then we convert that over with nice little simple tools that show you what the data representations look like, I think the model part is the easy part. I think that could just be a push button. I mean, it's like, how many people know how to write a compiler? You don't need to know how to write a compiler. Like, you just need to know how to write a certain language. Anyway, we touched on
so you're talking to the wrong guy. I have a compiler PhD. But,
well,
I think people should. I mean, look, I mentioned the NAND to Tetris thing. I think it's really, really important. I think it's really, really, really important that people have some understanding of all of the stuff that's underneath them. And this is why that world in which, you don't have to go all the way. This is the model where you say, I'm going to teach you how to build an AND gate out of MOSFETs. And then once you know how to do that, I'm going to teach you how to build an ALU out of NAND gates. And I'm going to teach you how to build a processor with around now a canned ALU. And you kind of have this idea that you kind of give someone some view of every level of the abstraction. It doesn't have to be very detailed. It's some view of every level of the abstraction. And once they've got the view of the abstraction, you can then abstract and you can build tiered abstraction. But what I always do worry about when we're trying to generate real computer scientists is where you have holes in the abstraction. And I do believe that every computer scientist ought to know how to write a toy compiler, because not very hard actually. And it's just I'm not sure I understand what the machine.
Well, it depends. I mean, I think the fundamental assumption you just made is that it's for computer science. So the thing that you're already talking about is they're already geeking. Talking about is how do you just get the average Joe to be able to do it, right? And that's what Ed Jongboom is trying to do, right? Trying to make people focus on the problem that they want to solve. And a couple of
we're trying to make computer scientists. This is the Raspberry Pi bias. Is we're trying to make computer scientists because as you know, a decade ago we realized we didn't have any, and therefore I'm probably still running down. Give you the numbers. 200 applicants for 100 places at Cambridge in 2008. To see if you want to get your kid into Cambridge in 2008, it's like not useful knowledge anymore. Get them to apply to computer science, a 2-to-1 ratio at Cambridge for a course. It's incredible. 1,400 applicants last year, so now not the same thing. So I think there is always a risk with all of these things when you get your head down and you're running forwards that you might end up like Wile E. Coyote, go off the cliff and you're still running in the same direction and you probably should have turned left 5 years ago. So biases. We should talk about biases.
So we've talked quite a bit about the education side. So coming back to some of the questions that folks have, they seem to be starting to dive into the technical aspects. So I'll start off with one, which is on the hardware side again. But how do you see vector extensions of RISC-V and ML embedded?
I mean, vector extensions are, I think, okay. So in all fairness, virtual hats off to the people at ARM who had this amazing realization that what we do in neural networks is a lot of vector math, and there is vector extensions already on the chip, and they built CMSSNN. This is so fucking brilliant and so insanely useful. So that's amazing. I think what ARM has done there is super cool. We see other vendors now follow suit. So if you look at the HiMax WE1 plus little dev kit, it's an ARC DSP, has vector extensions. They published the MLI library to do it as well. So virtually every target that has vector extensions is already using it. I think it's brilliant. 7 to 8 times speed up and no loss in accuracy. Unfortunately, Raspberry Pi 2040 is a Cortex M0 Plus. No vector extensions on that.
Although CMSys it's so well designed, actually. I mean, hats off. I'm going to take my hat off to a slightly different aspect of what our team has done, which is that they bothered to go and make it better for M0 Plus as well, right? Because there are things you can do to make it better. So there's probably a factor of 2. I think we found about a factor of 2 when we started using that code, even for M0 Plus. So yeah, it's an amazing team, and they've shown really amazing commitment to making this better across the entire spectrum of designs, from Cortex M0 Plus all the way up to things that have ethos accelerators in.
Yeah. That's cool. Yeah. And that's
RISC-V and specific thoughts.
Yeah. So, and that is one of the reasons why I think that RISC-V is a little bit behind at the moment and not so much used in NML. There's nothing like CMSS DSP, CMSSNN, like a high quality library with lots of signal processing and vector code like that for RISC-V. And I think that if a company like Sci5 or something wanted to do something really with ML and really want to go into the direction, I want something like that. So I think until we see that Eben maybe as a
vector extensions are interesting, right? I mean, talking again, I mentioned earlier the idea of this threshold we have for admitting pieces of hardware into the system. Vector extensions are really useful. They pass that screen much more easily because they are more general purpose, and therefore they are of use to you. You can put them in there and they'll be useful to someone who wants to go and decode video. We have Cortex A72 on on Raspberry Pi 4, it has full width, 4 cores, full width Neon. That's a lot of vector throughput, right? But that vector throughput can pay its way on the basis you can use it to decode video, or do lots of other things, and then it becomes a side effect. So I think that there is a world in which you're not getting the uplift that you get from dedicated hardware, but on the other hand, it is basically free in the system. And yeah, I do think there's value there.
Yeah, I think, but it always comes back to this, right? Which is like you need to have the proper library support to make it accessible, right?
Yeah, and that's really the RISC-V. That's really the RISC-V story, right? Software support. Software support. It takes time and needs investment.
And yeah, I was just gonna jump in. I actually helped write a paper back in 2019 that I've thrown the link to around using RISC-V extensions for machine learning with TF-Lite, and we have support for RISC-V. It's a very interesting community. One of the things I'm most interested in is I'm not generally a fan of FPGAs. They seem to be kind of the second best solution to almost any problem, is I think the mean thing that somebody once said about them. But they really shine when you want to experiment with potential hardware ideas. And there's a Google open source project called the CFU Playground, and don't ask me what CFU stands for.
Custom function unit.
That's right. Yeah, Vijay's been doing a bunch of work on this. But what I find really interesting is the tagline, which is "Want a faster ML processor? Do it yourself." And what that offers is a RISC-V soft core, as they call it, where you sort of compile a RISC-V core onto an FPGA, and the ability to easily run TensorFlow Lite Micro on it, together with a bunch of benchmarks and some pointers on how to add custom instructions to experiment with kind of ideas about sort of accelerating machine learning in ways that you care about, and being able to actually test it on real world examples. And for me, that's what's really interesting, is RISC-V kind of opens up the, again, it doesn't have the hardware support. It's not, there's a lot of negatives, but if you want to be able to have a chance to play with this kind of complete system, almost like kind of the whole stack, without having to spend, millions of dollars building your own, silicon, there's this chance to kind of play with it through this kind of thing. Like Eben was saying about, we want people to be able to understand everything. For me, that's a lot of the reason why I'm so excited about open source, is it actually gives you the chance to inspect every level. And this is being able to inspect a level that we can't normally inspect.
Yeah, I think that was always the sad thing about that XNOR stuff. You remember the XNOR stuff? That was really clever, but it was just a binary. It was doing clever stuff. They got bought by Apple in the end, didn't it? It was this clever, really clever black box, and you couldn't tell whether it was clever or not. Actually, it looked pretty clever, and it had a compelling, vague story around it. And it was just it was the most frustrating thing, because I'd always had it sort of felt like it was doing very, very reduced bit depth, like one bit. And I'd always joked that, I could see the way that I can do extrapolation as well as anyone. And, if we've gone from 32-bit floating point to 8-bit integer, I know where this is going. And then these guys show up with something that looks exactly as if they've actually gone to the place that I joked they were going to go, and then it got bought by Apple and vanished. But one day we will discover.
Well, I hope we can get to 0 bits. That'd
be perfect. It'll certainly be very energy efficient.
Well, on that note, talking about 0 bits, talking about energy efficiency, there are companies that are doing silicon photonics-based accelerators right now, right? Nothing in the embedded market space, but definitely in high-performance computing. Silicon photonics is one of the things that a lot of startups are, not a lot, but a handful of startups are looking at. Yeah. One thing I do want to come back to is some of the questions that folks have. Eben, I'm kind of curious. There's a question that's asking about, when do we expect the CPU shortage to finish?
Oh boy, Okay, so when do we expect the CPU shortage to finish? I would say Q3. Okay, I will now my colours the master say Q3 next year. On the other hand, I would have said 6 months ago, I would have said Q1 next year, right? So there is a little bit of this. It's a bit like becoming like nuclear fusion, isn't it? It's always 20 years away. I mean, I think fundamentally, what you've got to appeal to is if something can't go on forever, then sooner or later it will end. And the particular thing that can't go on forever is there's this notion of book to bill ratio in silicon distribution. This is the number of orders you're taking versus the number of things you ship out the door and bill. And that ratio is always between 0.95 and about 1.05. You know, it just bounces around in this collar around 1. It's been 2 for a lot of quarters now, probably for a year now. It cannot be 2. It cannot deviate from 1 for forever, right? And if it's 2 now, it'll need to be 0 for a while. So fundamentally, there's an imbalance in the force, and that isn't driven by end demand. It was driven by a shock. There's a thing called the beer game. I'm not sure if it's less fun than it sounds. You play the beer game? This is a little simulation for business school students of a pipeline in which people are, retailers are buying beer from a wholesaler, and the wholesaler is buying beer from a brewery, and everyone in the chain has to guess. And then there's a deck of cards at the start. Different business school students sit at different places in the pipeline, and at the start is actually a deck of cards that someone turns over to model consumer demand. And what happens is, because of the latency in the chain, the system's dynamically unstable and it just blows up. By the time you get to then you at the end of the game, you ask the guy running the brewery, what do you think happened? What do you think consumer demand was? And they were like, oh my God, there were people buying beer one day and then not buying beer for a month and then buying beer again. And actually all that comes in the front end is a step function. It's like 1 crate of beer, 1 crate of beer, 1 crate of beer, 2 crates of beer, 2 crates of beer forever. That's all that comes in the front end, right? And that's what's happened here, right? Is we had a step function. We actually had a sort of a drop because people thought nothing was going to happen. The economy was going to crash because of the pandemic, and then it stepped back up again. And what this has generated is these insane dynamics. It has to end fairly soon, simply because people are now hoarding, like people hoarded hand sanitizer and toilet roll last year. It has to end. People will run out of money. Fundamentally, you can only hoard. It's actually quite easy to hoard toilet paper because it's not very expensive. It's quite expensive to hoard FPGAs. People will run out of money. So I would say we probably have about 3/4 of remaining chaos. Of remaining shortage. The exit from it will not be smooth. The exit from it will be chaotic. We will build about as many Raspberry Pis this year as we built last year. That is very galling for me because the underlying demand has definitely gone up. I'm hopeful that we'll have another couple of fairly lean quarters, and then I think we'll probably be back in good shape.
Yeah.
Short question, long answer.
Hopefully, the answer itself as to when it'll end probably won't be that long. So hopefully.
The wonderful thing, of course, is RP2040. I don't sell from the stage, but RP2040 actually we are very lucky in that we do have a reasonable supply of that. We have a reasonable supply of that product. So I think probably a lot of our attention at the moment is in how we use those supplies to help some of these companies, a lot of them in the machine learning space, who have been starved by the traditional vendors.
Yeah. So, assuming that we don't have this shortage problem any longer in an ideal world, going back to the theme of like scaling embedded ML, I'm pretty sure a lot of people are curious about this. Like, Jan, specifically for you folks at Edge and Pulse, when you see people coming, customers coming through, what are the problems that they actually face? Is it things around the hardware that they actually face problems, or is it something about the data, or is it actually training the models?
So the customers that the commercial customers that we get in our pipeline typically already have a hardware platform selected and have supply chains already running. So the biggest thing where we can help is setting up. So the only way you can actually make decisions in any scenario, is my feeling, is if your feedback loop is short. Right? If you collect data now and only 6 months later you can draw some conclusions from it, then it's going to be really, really hard to fix something kind of early on. So we're an embedded ML platform, right? But if I see where our largest customers get lots of value from, it's data pipelines. So I'm in Aura did a presentation at our conference. The guys that make this sleep ring, they're using Edge Impulse to do all their data ingestion. So let's say they have someone in a hospital in Singapore that's going to sleep with like all kinds of sleep pads on their head and the ring on their finger. How do we know that basically the moment that that person wakes up, that the data is correct, frequencies were correct, the data lines up between the electrodes on the head and the data from the ring? How do we get like scoring of the stuff in quickly so we have reference data to cross that, and how do we feed that back into kind of our labeled data lake? Setting that up, that is it's very hard to build generic tooling for it because every problem that a customer has is different. The challenges are different, right? If one other customer does camera traps, and getting the raw photos of a camera actually involves a ranger driving to the camera, picking it up and swapping out SD cards, right? So helping the customer set the tooling up so that feedback loop is as short as possible, that is where I think we add a lot of value. And then iterating over those models becomes kind of a second nature because you can start running new versions of the model basically nightly. So yeah, that's definitely kind of number one reason why people pay us.
Yeah. Pete, I'm curious from Google's kind of perspective, right? Like, do you have any insights into what are the real problems around embedded ML?
Yeah, I mean, I'm not sure I can, speak for Google on this, but for me, it's really that there are all these people with really interesting problems out there that could be solved with, running ML on these embedded systems, but we aren't able to reach them.
Mhm.
Like, there's still this. I was going to say a gap. I think there's this like series of gaps that prevent us. Like we have all the ingredients to build these really interesting problem-solving devices, and for all sorts of reasons, like the software's too hard, the data pipeline, people don't have the kind of the understanding, they don't realize that their problems are actually now solvable and they couldn't have been, when they weren't solvable before. We haven't been able to get them into people's hands. So I see the most urgent thing as like, let's figure out how to get all this magic that we're collectively building. Like, let's actually get together and figure out how to give people something that they can actually use without having to get kind of a computer science PhD. Not knocking heaven, but
I drank a lot of coffee and learned to play a lot of chess. So
yes,
well. Didn't learn to play Go.
Yes,
but I did learn to play chess.
Can
I ask Pete a question? Can I nakedly attempt to get pointers for future hardware? Because I do spend millions of dollars on making silicon. Custom function unit. You got any hints for what custom instructions turn out to be useful for people?
What often happens is that people, honestly, it usually turns out that initially 90% of your time is going into convolutions and depth-wise convolutions. What's actually most interesting is the most common use case I've seen for this is we can actually do lower than, like we were talking about, lower bit depths and the XNOR stuff. And like even going down to 4-bit, there are not good standard, like we've lucked out in that signal processing actually needed to do a lot of 8-bit multiply adds. So we've got these awesome 8-bit multiply add instructions across a wide range of hardware. So as an industry, we've been like, cool, we can do like 8-bit weights and 8-bit arithmetic. But it turns out we can actually go down to like 4-bit weights and maybe like 8-bit or maybe 4-bit weights and 6-bit activations. But because we have no hardware that can actually natively execute that, we've ended up not really investing in we've kind of hit this point where it's not really worth training models at those bit depths because we can't run them on hardware efficiently. which means that the hardware people are like, oh, well, nobody's running models that are like, 4-bit or 6-bit. So, we don't really have to worry about that.
Now I can travel to the US. Do we need to go and get a beer?
Yes.
We need to go and get a beer.
Well, I've got a new niece back in Cambridge too, so I haven't
we get
seen...
We get 2 beers.
Yes, and I hate to say this, but we have better beer in the UK. So...
It's weird, right? If you want to have something which tastes incredibly of hops and has 8% alcohol, then Americans have better beer.
Yeah.
How do you? No, I always have this off topic, but I always have this thing about like, how do people these days go out and drink in America, right? Because you have one beer, it's like wine, right?
Yeah.
And you got to go out for the evening and you just drink water. You have one beer and then you drink water for the rest of the evening, or do you just go home at 8 o'clock? I remember when I used to live in America, it was all Budweiser, and you really literally can drink that stuff for 12 hours.
Oh yeah, no, it's like soda.
All right, folks, we got about 8 minutes. So one thing I do want to mention for this and more for the audience is that one of the reasons we wanted to have this scaling embedded ML kind of conversation is to try and identify what are some sort of problems and opportunities. I think one big thing that's kind of come out in some of the discussion that we've been having is like data is sort of a big thing, right? It's interesting because none of us have really been talking about building better models or really, what custom silicon do we really want, right? It comes down to just the data. So in order to kind of better understand, what kind of tools and things that we have to build, what we have done is we actually created a survey that I'm hoping that Artie or Sandra, who are working behind the scenes, will post. So this survey, if you could take a minute to fill out this survey, we would really appreciate it. Again, this is survey not to kind of just see what you're doing. It's more about helping us kind of figure out what tools and infrastructure we actually, as a community, need to be building. So the survey basically goes and asks a whole bunch of range of different kinds of questions. How do you use data? Where do you get your data from? It also talks about what kind of systems do you use so that, we can all, as a community, build better tools. So I'd appreciate it if folks can actually go ahead and fill the survey out. And thanks to several sponsors, there are actual prizes that will be given out for filling out the survey. You will certainly see it on the page, so I won't get into the details there. But I know we're going to be having to stop soon, so please do make sure you fill the survey out. Now, coming back to the group again on this topic, if I was to ask each one of you, right, what is the single most important thing that you want to, okay, maybe not one, maybe it's 3. What are, like, say, the top 3 problems that you think you see in facing embedded ML deployments that we have to solve as a community? Starting off, maybe Jan, jump in.
Yeah, so number 1 is confidence in your model. That's kind of, I'm actually going to keep it at only 1. Confidence in model, right? Even if you train something and you have 98% accuracy in your test set, what the fuck does that mean? Does that give you confidence to put that into a critical life support system? Probably not. Is it enough in a white goods device? Probably not, because you need to know the strengths and the weaknesses of the model. So we're working a lot right now, like on features to improve that confidence. So we call it application testing. Basically gives you like a day's worth of data